Hello, everyone. Welcome. Happy Wednesday to you. Hope you're doing well. Playing a little salsa music there by a couple of my favorite Cuban artists, Willie Chirino and Hansel. They're kind of a little old school, so you might not hear them in recent times, but they're popular when I was a kid, and I still love to listen to them. So thanks for bearing with me and listening to my music. It's fun to share it. Okay, well, we are progressing very nicely. We are right on schedule. I hope you guys feel the same way. I hope you feel like you're sticking with it. Remember, as I said before, this is the time to really stay on schedule. Okay, just stay with the material, and you will get this. All right. So we are jumping into the chapter on acids and bases now. All right. So that's chapter 17. And it's about acids and bases. And you'll see we're going to continue to use the equilibrium principles that we learned about in the last chapter in this material. So this is just a little cartoon based on a based on the Batman comic book series. In one of those series, there is a villain called Black Mask. If any of you read comic books, maybe you've heard of Black Mask. Anyway, he's a villain in Batman. And at one point, Black Mask gets squirted in the face with acid, and the acid begins to burn through his mask, right, and into his skin. And Batman, being the nice guy that he is, even tries to help the villain. And so he says, "Don't worry, Mask, this base will neutralize that acid," and he squirts him down with base. And well, of course, it is true that bases neutralize acids, right? That is indeed true. But that was, in fact, a mistake. You wouldn't do that in a lab. If you, it's not. This is kind of a redo of the comic book. I couldn't use the actual comic book because that would be illegal. So this is just kind of a drawing that represents that. Anyway. If you ever spill acid on yourself in lab, you don't put base on it. What do? Does anybody know? Can anybody tell me?
Do you usually put water on it?
Yeah, you rinse with water, okay? You just rinse with a lot of water. That's the key. And there's two reasons you don't put a strong base on an acid. One is the reaction between an acid and a base is extremely exothermic. What that means is that it produces a lot of heat, right? So even though the base might not burn you, the heat from the neutralization reaction might. So you're better off just washing off the acid. The second thing is that you'd have to get the amount of base exactly right to exactly balance stoichiometrically the amount of acid. Otherwise, you end up with the opposite problem, right? Because if you don't squirt enough base, of course, then you wouldn't neutralize all the acid. And if you squirt too much, then you'd have extra base, and then the base could be a problem, right? So this is not the solution, Batman. Okay, next time just squirt them down with water. You'd be way better off. All right, so let's jump into this chapter. I see there's a quick question here, Taylor.
So would you get a base burn?
Yeah, a strong base can also burn your skin.
Oh God.
Yeah.
Wow.
Absolutely.
Okay.
Yeah, you don't want to spill strong base on yourself either.
Okay.
Concentrated, actually I should say concentrated. Concentrated acids and bases are things you got to be careful with, right, in the lab. Okay, so let's start. We're going to look at some properties of acid bases, some definitions, and we're going to see how they have their own equilibria, right? And hopefully we'll look at the autoionization of water and pH. So that's kind of our plan for today. So some properties of acids. So first of all, acids have a sour taste, right? Acids are common in many foods that we eat, right? Who can mention a couple of foods that might be acidic?
Any citrus?
Lemons.
Citrus, right? All citrus fruit like lemons and limes contain acids. What else?
Vinegar.
Vinegar, yeah. Vinegar is acidic. And so that sour taste that you taste in those foods is from Doritos. It's from the acid. Your stomach actually contains quite a bit of acid because the pH of your stomach needs to be acidic in order for the proteins that help digest your food to work properly. So sometimes if you get heartburn or you feel like or that sour taste in your mouth, and this is kind of gross when you throw up, right? That's due to the acids in your stomach, right? If you have acid stomach and heartburn, what do you take to counteract it? You actually take a base to neutralize it. But you take a special kind of base that will neutralize the acid as it forms more base. And we'll talk a little bit more about that a little bit later, all right? But you wouldn't take a strong base because a strong base would burn your mouth, right? So you take something like calcium carbonate, which is the active ingredient in Tums, or magnesium hydroxide, and these things will fall into your stomach and then begin to neutralize the acid instead of just acting as a base immediately. So, okay, acids have this sour taste. Acids react with active metals. So in some spy movies, you'll see like a spy gets, like James Bond gets trapped in a prison, right? And he'll pull out sometimes like a gold pen, and it'll contain an acid, and he'll squirt the acid on the bars, right? And that's how he'll escape from prison, right? Have you seen this in any spy movies? Anyway, it's a common theme. And it is true, acids will dissolve metals like that, all right? Now, whether or not you can fit enough acid into a gold pen to dissolve an entire iron bar, well, I don't know about that, but the idea is sound. Acids do dissolve active metals. Not all metals. There are some metals that resist acids, and we'll get to those a little bit later in this course. Acids react with carbonates. So acids will react with things like concrete, for example, and dissolve the concrete, or it'll react with things like marble and dissolve the marble. That's why acid rain can be a problem for statues and structures, right? The acids in acid rain can dissolve some of those, right? Acids turn blue litmus paper red, all right? And so if you've, in the lab, one test to see if a solution is acidic is just dip some litmus paper in it. If it turns red, then you know the solution is acidic. If it stays blue, then you know it's basic. And then lastly, acids neutralize bases. Yeah, limestone is correct. Limestone acids will dissolve limestone. And then lastly, they'll neutralize bases. Here are a few common acids: hydrochloric acid, HCl. It's used in metal cleaning, food preparation. It is one of the acids that's in your stomach, okay? Here's acetic acid right here. You can read these in your book. I'm not gonna go through all of them. Acetic acid is the active ingredient in vinegar, okay? Citric acid, this is the acid in lemons and limes. Carbonic acid, this is the acid that occurs in anything that is carbonated, like soft drinks, for example. They'll have carbonic acid. Hydrofluoric acid is one of the more dangerous acids, partly because the hydrogen is very small and fluorine is one of the smallest halogens. And so it can seep into your skin very quickly. And actually it's called a bone seeker. It gets through your skin into your bones. It starts dissolving your bones from the inside out. Isn't that awful? So if you ever see HF, just stay the heck away from it. My nephew's a firefighter, and he's been in situations where they've spilt this on the ground. It's very, very, very dangerous. Stay away from that. You just only people in complete hazmat suits and things like that can go in and clean something like that up. Okay, so what are the structure of acids? What do they look like? Well, binary acids, which we already learned how to name. Well, we already learned how to name all acids, but binary acids, remember, have hydrogen and they're attached to a non-metal. So things like HCl and HF are both binary acids. So here's hydrochloric acid, for example. Oxyacids, right, are usually hydrogen or one or more hydrogens with a polyatomic ion. And the polyatomic ions in oxyacids are, of course, oxygen containing, right? So this is the SO42 minus ion, right? And this is sulfuric acid. This is the nitrate ion, and this is nitric acid. And their structures, or Lewis structures, look something like this. In this case, sulfur's in the middle with 4 oxygens and then 2 hydrogens. And it's these hydrogens that are the acidic hydrogens responsible for the acidity. And this is nitric acid. Again, you see nitrogen surrounded by oxygens with a hydrogen. There is a class of acids called carboxylic acids. Carboxylic acids are the acids that you find in organic substances. So things like the acids in lemons and limes, for example, are carboxylic acids. Acetic acid that you find in vinegar is a carboxylic acid. We're usually going to write these formulas like this: HC2H3O2. It's hydrogen plus some ion. All right. Sometimes you can have more than one acidic hydrogen. So for example, here you can have 3. So it's H3C6. But notice I'm separating these hydrogens from these. Why is that? Because these are the acidic ones, and these are part of the polyatomic ion. So here's what a carboxylic acid group looks like. C double bond O, OH. That's why you write it COOH like this. And then it usually is attached to something else on this side. Taylor.
Does the more acidic hydrogens, do they make the substance more acidic?
Not necessarily.
Okay.
Because as we're going to get to in a minute, there are strong acids and weak acids. And most of these kinds of acids that have more than one proton tend to be weak. So some of the strongest acids are monoprotic acids like HCl, for example.
2 elements.
Yeah. Although sulfuric acid, although nitric acid, we'll get to that. We'll get to that in just a second. Yeah.
Okay, cool. Thank you.
On the opposite side, chemically speaking, we have bases. So bases are also known as alkalis. Bases have a bitter taste. Okay. Part of the reason for their bitter taste is that many organic poisons are basic. And unlike the sour taste in acids, which oftentimes is enjoyable, right? So people add lemons and limes and vinegar to things all the time, right? Because we enjoy that sour taste. The bitter taste of bases is usually not very enjoyable, at least not at first. Sometimes it's an acquired taste, but typically we don't like the taste of bitter. And that's because many organic poisons are actually bases, right? So for example, hemlock contains the active ingredient in hemlock that ends up killing you is an organic base, okay? And so that bitter taste is associated with those things, and it basically is a protective, evolutionarily protective sort of response, right? We don't tend to eat those things that taste bitter because some of them turn out to be poisonous, okay? If you've ever, now, sometimes bitter taste can be acquired over time, so you can start to like the bitter taste. For example, some beers can be bitter, but usually the first time you taste a bitter beer, you don't like it very much, right? But over time, you can acquire a taste to it. Some dark chocolate is bitter, right? And again, same idea. There's some bases in there that produce that bitter taste, and over time you can acquire sort of a taste to it, but it's not naturally something that a kid's gonna say, oh, I love that give me the dark chocolate instead of the milk chocolate, right?
Wait, Tro, what about like grapefruit? They're pretty bitter, but aren't they also acidic too?
Yeah, so sometimes you can have, surprisingly, you can sometimes have both. You can have the acidic taste and the bitter taste from a base, and even though they neutralize each other to some degree, the flavors aren't completely neutralized. So for example, coffee can be bitter and acidic because you have, so caffeine is itself a base, right? And it's responsible partly for the bitter taste of coffee, but coffee is generally speaking acidic. So they neutralize each other to some degree, but the flavors don't totally get neutralized. So even though the acidity and basicity of them can change, the flavors of those compounds that are basic continue to taste bitter. One time when I was a kid, I played this terrible joke on my little brother. You know how it is when you're a kid and you like start discovering like new foods, and all of a sudden it becomes the latest craze, right? You discover some new food as in your family or with your brother, and you're like, oh my gosh, I want it all the time. So we had kind of discovered white chocolate for the first time. So my brother and I were always like, oh, Mom, take us to the candy store so we can get some white chocolate, right? And so one day I got this terrible idea where I took one of these white soap bars and I kind of cut it up so it looked like that chunked white chocolate, and I gave it to my little brother. And he was like so happy that I had given him chocolate, and he like puts it in his mouth, and all of a sudden he's like, "Wah!" Starts crying, and he was like so mad at me. And of course I got in trouble. It was terrible. But anyway, soaps are basic, and they taste bitter. I know, wasn't that that was terrible? I'm much better. I'm much nicer to him now. But when I was a kid, sometimes I was kind of mean to my little brother. Anyway, that slippery feel of soap is also happens with bases. What happens is when you spill a base on your fingers, it'll actually form soap from the oils on your skin, and you'll feel that kind of slippery, soapy kind of feel. So solutions that are basic will tend to feel very slippery.
Why do they feel slippery?
Because they actually react with oils in your skin and create soap on your skin. So the way to make soap is usually you take oils or fat and you add base, and that ends up carrying out some reactions that create the soap. So the same thing happens when you spill base on your skin. Bases turn litmus paper blue. All right, an easy way to remember that, basic blue. They both start with B. And then finally, they neutralize acids. Ryland.
Do you know if there's a reason that like plants evolved basic poisons instead of acidic poisons? Is it easier? Are they more effective?
Good. Yeah. So the bases are poisons not because they're bases. So it's not their it's not their ability to produce hydroxide ions in water that kills you or poisons you. It's the amine. There's a nitrogen containing component to a lot of poisons and actually a lot of drugs. So you've heard of methamphetamine or amphetamines, and a lot of drugs are actually organic bases. So these organic bases, not just kind of a coincidence that they happen to be basic, but they also have a lot of metabolic activity, I guess. And so the part of the basicity of the compound is not the problem. It's the way it interacts with proteins and things like that.
Got it.
Does that answer your question? So it's just kind of a coincidence, I guess. But of course, it's a coincidence that you're. Professor Eric can explain it really well. Okay, good. Maybe you can type a quick explanation into the chat, Zuo, if you don't mind. Because I don't know the details of the biological interactions. All right, what else do we have here? Some common bases: sodium hydroxide. You know, when you go to the hardware store and you see lye, that's sodium hydroxide. Potassium hydroxide. So sodium bicarbonate. This is the active ingredient in baking soda. Okay, so baking soda contains sodium bicarbonate. Ammonia is a common cleaner that you might use around the house, right? And then sodium carbonate here. Most ionic bases are going to contain hydroxide ions like sodium hydroxide, calcium hydroxide. Some bases contain the CO3 2- ion like calcium carbonate and sodium carbonate. We'll see later how these ions act as bases. And then molecular bases contain structures that react with H+ groups, and those are mostly amine groups, which are this nitrogen-containing compounds. All right, nitrogen-containing organic compounds, and we'll see some of those in a minute. Okay, so those are just some of the general properties of acids and bases. Let's jump into some definitions of acids and bases. So turns out there are several different kinds of definitions. We'll start with this one called the Arrhenius definition. And in this definition, an acid produces H+ ions in solution, and a base produces OH- ions. So an example of an acid would be hydrochloric acid, which when you put that in a solution, it forms H+ plus Cl-. An example of a base would be NaOH. When you put that in a solution, right, it produces Na plus plus OH minus, right? So HCl is a classic Arrhenius acid, and sodium hydroxide is a classic Arrhenius base. So in these formulas, remember, we're always going to write that acidic hydrogen out front. Okay, so here's acetic acid, and it dissociates to form H plus and C2H3O2 minus. Okay, so you can see it follows the same pattern as HCl, right? So we're going to see this kind of equation quite a bit. So Arrhenius acid, like HCl, you put it in solution, it completely. We say that acids ionize, whereas ionic compounds like sodium hydroxide, we say they dissociate. Why the difference? Because ionic compounds contain sodium plus ions and OH minus ions, right? So when they go into water, they don't have to form the ions, they just fall apart, they dissociate, and the ions become basically separate from one another, right, in water. Here, HCl is not an ionic compound, right? HCl is a molecular compound. So HCl doesn't really contain any ions, but when you put it in solution, it ionizes, right? It forms ions, forms H plus ions and Cl minus ions. That's why we say with acids, they ionize in water, whereas with ionic compounds and bases like this, we say they dissociate in water, okay? Now, H plus on its own does not really exist in water. It actually will associate with a water molecule and form H3O plus. So a lot of times chemists will write H plus or H3O plus, and those are both essentially the same thing. Okay, so those are completely equivalent to one another. If you see H plus, that really means H3O plus, okay, because it always exists as H3O plus. Here's the Lewis structure of H3O plus. This ion is called the hydronium ion, okay? And again, any acidic solution, that's what it's going to have in it. All right, second definition of acids and bases. Under this definition, an acid is a proton donor, and a base is a proton acceptor. And so in an acid-base reaction, you get an acid like HA reacting with a base B, and it's going to form B. Let me see, I want to write this the same way every time. It's going to form BH plus A minus. Okay, and here, right, notice what happened. This proton was donated to that base, right? So this is the acid and this is the base, all right? In the Bronsted-Lowry definition, we also have conjugate acids and conjugate bases. So you figure though, you can think about what would happen in the reverse reaction. In the reverse reaction, this becomes the donor and this becomes the acceptor. Right? If you think about this reaction going in reverse, this becomes a donor and this becomes acceptor. So we call this the conjugate acid, and we call this the conjugate base. And these two together, let's say HA, A minus, or B, BH plus. These are called conjugate pairs. Those are called conjugate acid-base pairs. This is one pair, right? This is one pair. And there are two things like this that are related to each other simply by the transfer of a proton, okay? So notice that to go from here to here, right, you lose a proton. To go from here to here, you gain a proton, right? So this is an acid-base, conjugate acid-base pair. This is an acid-base pair. So let's look at this reaction. H2O plus NH3 goes to OH minus plus NH4 plus, right? What's acting as the acid here? In the forward direction. H2O, right? H2O is acting as an acid, becomes OH minus. NH3 accepts that proton, so NH3 is the Bronsted-Lowry base. Okay? And then you can see these two together are a conjugate acid-base pair. Ammonia here is acting as the base, and so NH4 plus is its conjugate acid, right? So this is the conjugate acid-base pair. Okay. So in every case, let's look at this. Here's another example of a reaction. Here's HCHO2, right? That's the acidic hydrogen right there. In this case, water is acting as the base, right? So it transfers the proton over and you get the conjugate base. Notice the acid conjugate base, and you got your base and your conjugate acid. Notice here, water is acting as a base. Here, water is acting as an acid, right? Notice it's donated a proton to NH3 to form NH4 plus. And when it loses that proton, it becomes OH minus, right? So you got acid, base, conjugate acid. Does that make sense? Questions? Okay, let's do a little practice and then I'll ask you a question. Let's write the formula for the conjugate acid of each of these things, right? So we got H2O. What would be the conjugate acid of H2O?
H3O plus.
Correct. Just add a proton, right? What would be the conjugate acid of NH3?
NH4 plus.
Correct. What would be the conjugate acid of CO3 2 minus?
Wait.
It'd be 2HCO3.
Yeah, so if you just, usually it's only one proton. So you would just add one and you'd end up with HCO3 minus.
Okay. I was
Right.
thinking the same thing.
So that's the conjugate acid of that base. And then what about H2PO4 minus? What would be the conjugate acid of that base?
H3PO4.
Correct, H3PO4. Does that make sense? Taylor?
I just had a question from earlier.
Yeah.
Is the HO2 and the H3O, or yeah, the H2O and the H3O, do they behave the same or are they
No.
kind of different?
H2O is just plain water. H3O plus is the hydronium ion, which is responsible for the acidic behavior. So this is the thing that has the sour taste, that dissolves metals, that does all that stuff.
Okay. And then when it does associate with someone or something, it just turns into normal water again, or?
It can turn into normal water if it reacts with a base and just gets neutralized.
Okay. So it's just
Right.
in that state temporarily, or it's kind of like,
It's not really, you can have a stable solution of, like if you just have, so I know I showed you this earlier with all these H, so this is a stable solution of hydrochloric acid, right? All these H pluses that I have in here are really not H plus, they're really H3O plus, right? Because H plus doesn't really exist by itself. Okay, but a lot of times we'll write it this way, even though that's not really the way it exists, just because it's easier.
yeah, okay, that makes sense.
Right, so
Yeah,
you can
I know
have
there's-
you can have a stable solution with a bunch of H3O plus in it. It's not
Okay.
temporary, it's just what it is. It's an acidic solution.
Okay. But the liquid doesn't like really act differently. Like it's not like,
It will act, I mean, it would look like an HCl solution would look like water, but it certainly wouldn't act like water chemically, right? If you
Okay.
spill water on your skin, you'd be fine. If you spilled this on your skin, you'd be burning your skin, right? If you put
Yeah.
aluminum into water, nothing would happen. If you put aluminum into this, you'd get a big bubbly reaction and the aluminum would dissolve away. Does that make sense?
Okay. Yeah, that makes sense now. Okay.
All right, so here we wrote the formula for the conjugate acid. Now let's write the formula for the conjugate base of each of these. So what's the conjugate base? So this is conjugate acid up here. All right, and here is conjugate bases down here. What's the conjugate base of H2O?
OH negative.
Correct. To get the conjugate acid, you add a proton. To get the conjugate base, you remove a proton, right? What's the conjugate base of NH3?
NH2 minus.
Correct. What's the conjugate base of CO3, CO3 2 minus? Trick question, that one doesn't have one, right? Because in order to get to the conjugate base, you have to be able to remove a proton. Does this have any protons? No. Okay, so this doesn't have a conjugate base. Not everything has a conjugate base. H2PO4 minus, however, does have a conjugate base. What would that formula be?
That'd be HPO4 2 minus.
Correct. HPO4 2 minus. Does that make sense? All right, here's a question for you. Go ahead and try to answer this question. Okay, looking good. Almost all of you are getting this right. So I'm going to give you a couple more minutes, another few seconds. I'm going to stop it. Okay, the right answer was D, and look at that. Most of you got that right. So nice work. Remember the reason each of these are related to each other by the transfer of a proton, right? So this is the base, that's the conjugate acid. This is an acid, there's the conjugate base. There's an acid, there's a conjugate base. But these are not related to one another by the transfer of a proton. Notice they both have one proton. These have a different number of oxygens, okay? So that's not a conjugate acid base pair, all right? So the right answer was D. Nice work. Okay, let's try one more. All right, 10 more seconds. Nice. Look at that. Has that happened yet this semester? Nice work. 100%. Thank you. Yeah, 90% of you voted and 100% of you got it right. So, wow. I should just stop right there. No, that was awesome. Thanks, you guys. That makes me super happy. All right, let's move on. HSO4 minus. Was there a question? Oh, Ryland, you have a question?
Yeah, it was about the previous one.
Yeah.
I was a little confused as to, because to me it looks like there's 9 hydrogens. Oh, and then 10 hydrogens. Never mind. I just needed to look at it one more time.
Oh, so yeah. So remember these so the hydrogens that aren't like on a base, you usually put on bases that contain ammonia, you'll usually put the proton out here of the conjugate base. So it's H plus. So it's H plus. So these hydrogens are not neither acidic nor basic. So that's why. Okay. Very good. Yeah, I like that. All right, so let's jump into acid strength and Ka. So there are 2 kinds of acids, strong acids and strong acids completely ionize in water. What do I mean by that? I mean that if you put a mole of HCl into solution, it'll completely ionize, so you have a mole of H3O plus and a mole of Cl minus, right? You won't have any undissociated or unionized HCl in solution, right? So, for example, HCl here, right? We're going to draw it with a forward arrow only. I'm not going to draw a back arrow to indicate that this reaction goes to completion, right? If I have a mole of HCl, I'm going to have a mole of H plus. And these 2 reactions mean exactly the same thing, right? The only difference is that here I'm writing the water explicitly, and here I'm just leaving it out because I'm too lazy to write it, all right? But these are exactly the same thing. HCl plus H2O goes to form H3O plus Cl minus. This is a little more accurate in terms of what's really going on, but chemists will write this all the time to mean exactly the same thing, okay? There are 6 strong acids that I want you to know, that I want you to memorize. HCl, HBr, and HI. And then HClO4, HNO3, nitric acid, and H2SO4, okay? These are the 6 strong acids. Any other acid that you see, so in other words, anything else that you see written in this form, you can assume is a weak acid. All right? These are the 6 strong acids, and anything else you see, you can assume to be weak. All right? Weak acids only partially ionize when you put them in water. So hydrofluoric acid, for example, is an example of a weak acid. And what I mean by that is that if you look at a solution of HF, you'll find a lot of HF molecules, right? And only some of them will have ionized to form F minus and H3O plus, okay? Usually less than 10% of them, all right? We can characterize weak acids by their acid ionization constant. So I am going to, the main equation here that I want you to know is this one. H2O goes to, in equilibrium, with H3O plus A minus. This is the generic equation for a weak acid. Okay. Generic weak acid. This is one of 4 equations that need to become your best friends in the next couple of weeks. All right. This is the first of 4. So I'm just going to number it number 1. All right. And we'll see the other ones as we go along, but there's 4 very important equations moving forward that'll be key to understanding the things that we're doing. And this is one of them. It's the ionization equation for a weak acid. All right. And as all equilibria, this has a K associated with it. We call it Ka, the acid ionization constant. And it's equal to the concentration of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients, right? Does that sound familiar from last chapter? Hopefully it does, right? Of course, water here, and I've left that out. Water is a liquid, so we don't include it. These are all aqueous, so we include all of those. And this then is a measure of the strength of the acid, right? For strong acids, we don't worry about, so for example, HCl, we can write the same equation. Right, as this generic equation. We can write it for HCl, but for HCl, this forward arrow tells you that it goes to completion. So K is some huge number that we don't even have to worry about because it goes all the way to the right, okay? But for weak acids, K is a measure of how weak the acid is or how strong the weak acid is, okay? So there can be some weak acids that are stronger than others, all right? And yes, HF is a weak acid, but it's a very dangerous weak acid for the reasons I talked about. These are the only 6 strong acids. Any other acid you see other than these, you can assume is a weak acid, all right? So here are some weak acids, and there are a lot of them. That's why if you just memorize the 6 strong acids, then everything else you see is weak, okay? Here's HF, weak acid, right? Its Ka is 6.8 times 10 to the minus 4. So you can see there are some weak acids that are stronger than HF, right? Here's chlorous acid. It's stronger than HF. And then there are some weak acids that are much weaker, all right? Notice for a lot of these, you see this group right here that I talked to you about before. That's the carboxylic acid group, right? C double bond O, OH. This is present in most organic acids. So here's another organic acid, benzoic acid, C double bond O, OH. Here's acetic acid, right? The acid in fertilizer, right? So you'll see that structure a lot. And these are the Kas. So this acid, for example, hydrocyanic acid, is much weaker than chlorous acid, all right? The smaller the K, the weaker the acid. Does that make sense? All right, very good. Now, let's talk about water for a minute, because we've already seen in some of the reactions, water was acting as an acid, and other reactions, water was acting as a base. So water is what we call amphoteric. Can act as acid or base depending on what it's reacting with, right? So for example, if you put hydrochloric acid with water, water acts as a proton acceptor. It acts as a base, okay? But if you put water with ammonia, water acts as an acid. Right? It donates a proton to ammonia. Okay. This is an example of the second equation that's going to be very important for you to remember. So I'm going to write that one down as number 2. This is generic weak acid equation, and here's the generic weak base equation. And it follows this pattern. And I'm just going to write it down now and we'll come back to it in a minute. Base aqueous plus H2O liquid in equilibrium with BH plus OH minus, right? So most weak acids are going to act according to this equation. Most weak bases are going to act according to this equation, all right? I'm going to set that aside for right now, but I just wanted to put it on paper. These two equations right here. Just, I know you have a cheat sheet and everything on the exam, but you should just commit these to memory because you're going to be using these over and over and over and over again, okay? And they're super important. So make these kind of like I said, kind of like your best friend. Since you can't see all your friends right now, you can at least see your acid-base equations, right? Pretty exciting. Although things are getting better, right? Cases are coming down. People are getting vaccinated. Schools are opening. Have you heard about this? They're going to open elementary schools. Oh, it's so great. I can't wait till they open SBCC. As much as I love teaching this way, just kidding. I don't love teaching this way. I'd rather teach in real life. So I can't wait for things to open, especially SBCC. Okay, so water acting as a base, water acting as an acid, and here's water acting as an acid and a base with itself. Okay, so this is called the autoionization of water. If you just have a sample of water, you get, you guys are cracking me up. I keep looking at the chat and it's just distracting me and making me laugh. And I'm supposed to be teaching, so that's okay. I like it. Don't stop. My wife is a school teacher, but she teaches at a private school, so they've been open all year. They've been open since the fall, and so far so good. They haven't had any issues. Everyone wears a mask and they say her main challenge is she teaches middle school. She teaches middle school science, right? So she has to keep these middle school students 6 feet apart. Imagine that. That's the hardest part of her day. It's like teaching math and science, that's easy. Keeping these kids 6 feet apart, forget it. Oh boy. All right. Where was I? Water acting as both an acid and a base right here. So it auto-ionizes itself, okay? Notice here what happens. This acts as an acid. It gives a proton to here, and it forms H3 plus and OH minus. Now, if you just have a beaker of water sitting there, okay? This reaction happens, but it happens only a very tiny amount, right? Most of the water molecules stay as water, all right? So you have H2O. Let me just write this down. This is liquid. This is liquid. H3O plus, aqueous, plus OH minus. So the equilibrium constant for this reaction is called Kw. And or sometimes it's called the ion product constant for water, Kw. And it's, of course, it just follows the definition of all equilibrium constants, right? The concentration of the products.
Can you scoot the paper up a little bit?
Oh yeah, sorry. Thank you. Concentration of the products raised to their stoichiometric coefficients divided by the concentration of the reactants, but the reactants are both liquid, so that's all it is, okay? And this can be measured, and what do you think? Is it a big number or a small number?
Big number?
So remember what I said, most of the water molecules remain as water, right? Only a very small fraction of them do that. So what do you think?
Small number.
So it's a small number.
Right. 10 to the minus 14, a very, very small number. Okay. So that tells you that the reaction doesn't occur very far to the right, right? In water, in pure water, most of the molecules are water, right? But a small number of them are going to ionize like this. All right. Now, notice that I can say, oh, okay, I can set up an ice table. and I can find out the concentrations of those, right? In equilibrium with H3O plus OH minus, initial change equilibrium, 0, 0, plus X, equilibrium XX, right? And so what do I have? I have X squared is equal to 10 to the minus 14, right? So X is equal to 10 to the minus 7, right? So in pure water, the concentration of H3O plus is equal to the concentration of OH minus is equal to 10 to the minus 7 molar. Very, very dilute, right? So again, not very much, only a very small fraction of the water molecules are going to do that. Okay, but this equation, right? The expression for Kw is true for any aqueous solution, right? So what I mean is that the concentration of H3O plus times the concentration of OH minus will always be equal to 10 to the minus 14, okay? So what does that mean? If I add H3O plus, if I add acid to a solution, H3O plus goes down, what happens to OH minus? Sorry, back up. If I add acid, like if I add HCl to a solution, H3O plus goes up, what must happen to OH minus? Goes down, right? Or vice versa. If I add base to a solution, OH minus goes up, and what happens to H3O plus? Goes down. But it'll always be the case that this product is 10 to the minus 14. So in any solution, if you know one of these, you know the other one, right? If you know H3O plus, you can find OH minus. If you know OH minus, you can find H3O plus, right? Because they're equal to 10 to the minus 14. All right. So all aqueous solutions contain both H3O plus and OH minus. Neutral solutions have exactly equal amounts, right? H3O plus and OH minus are equal, and they're 10 to the minus 7 molar. Acidic solutions have H3O plus that's more than 10 to the minus 7 and OH minus that's less than 10 to the minus 7. Basic solutions have H3O plus that's less than 10 to the minus 7 and OH minus that's greater than 10 to the minus 7, right? So let's think about completing this table. If up here I write different H plus concentrations, and again, remember H plus, H3O plus, they mean the same thing, right? So if H plus, I already know, if H plus is 10 to the minus 7, what's OH minus?
The same.
The same, right? 10 to the minus 7, okay? But if H plus is 10 to the minus 1, then what's OH minus?
10 to the minus 13.
10 to the minus 13, right? So if you know any one of these, and if H plus is 10 to the minus 13, then OH minus is
10 to the minus 1.
10 to the minus 1, okay? So you can complete this table. Right here is a neutral solution. It has exactly equal amounts of H plus and OH minus, 10 to the minus 7, right? As you get on this side of the scale, you're talking about solutions that are acidic. And they have more than 10 to the minus 7 molar H plus and less than 10 to the minus 7 molar OH minus. On this side, you have basic solutions, right? Less than 10 to the minus 7 molar H plus and more than 10 to the minus 7 molar OH minus, right? This forms the basis for what we call the pH scale, okay? The pH scale is a way to express acidity, and it's defined as minus the log of the H3O plus concentration. Okay, minus the log of the H3O plus concentration. So remember that a neutral solution has H3O plus equal to 10 to the minus 7, right? So pH of that solution is equal to minus the log of 10 to the minus 7, which is equal to 7. So a pH equals 7 to neutral is what we call a neutral solution, right? It would correspond to this solution. Okay. What would be the pH of a 10 to the minus 1 molar acidic solution? Well, it would be minus the log of 10 to the minus 1, right? Remember, when you take the log of something, it's what number do you have to raise 10 to get that number, right? So that's equal to 1, because minus 1 is 1, right? So the pH of this solution would be 1. So here's the pH scale. Here's the H plus concentration, 10 to the minus 7, right, is neutral. That's pH of 7. Here's my 10 to the minus 1 solution, pH of 1, right? 10 to the minus 0, pH of 0. All right, so you can have this pH scale. 7 is neutral. Anything above 7 is basic. Below 7 is acidic. Above 7 is basic. pH of 7 is basic, right? You ever taken the pH of pool water, right? Usually try to get it to be neutral, right around 7. And this is the scale that that's measured on. Okay, just to give you some references for some pHs of things that are familiar. Rainwater, so pure water has a pH of 7, but rainwater contains dissolved carbon dioxide, and dissolved carbon dioxide actually forms carbonic acid, which is acidic. So even just unpolluted rainwater has a pH that's slightly acidic, 5.6. All right. Here you see some other things. So things like lemons and limes have pHs in the range 1 to 2, 2.5. Okay. The juices in our stomachs, pH 1 to 3, right? Some basic things, our blood is just very, very slightly basic, almost exactly neutral, but just a tiny bit basic. Egg whites, milk of magnesia, which is what you might take for heartburn, is basic, right? It neutralizes some of the stomach in your acid in your stomach, some of the acid in your stomach. Ammonia, sodium hydroxide solution. Yeah, all rain is acidic, but is naturally acidic, but that's not really a problem because it's not very acidic. It's only when you get there are some pollutants like nitrogen oxides and sulfur oxides, and those pollutants come primarily from fossil fuel combustion and especially electricity combustion from coal. So the middle part of our country has a lot of these coal burning power plants that produce electricity. They produce nitrogen oxides and sulfur oxides that can get up into the atmosphere. When those mix with water, they form sulfuric acid and nitric acid, and then that can fall as rain. So this problem, acid rain, is primarily a problem in the eastern United States because of the way the jet stream flows. Interestingly, we've been able to pretty much almost solve acid rain problem. I've been tracking acid rain for about 20 years, 25 years. 25 years ago, it was a big problem. pHs of rain could be things like 4, 4.5 in the eastern United States. It caused damage to forests. It can harm ecosystems. It can dissolve building materials. But we've put in legislation that required these power plants to put scrubbers in and catch the sulfur oxides and nitrogen oxides that come out. And now the pH of rain in the eastern United States is almost back to normal. Not quite, still a little bit of a problem, but it's way better than it was 20, 25 years ago. That's thanks to the Clean Air Act and its amendments. So good legislation cleaned this problem up. In fact, good legislation has cleaned up a lot of air pollution. Things like, for example, nitrogen oxides that were over LA, for example, or lead in the air, or ozone. All of these pollutants, compared to where we were 25 years ago, have come way down thanks to the Clean Air Act and its amendments. So we're making progress on some of these things, which also, by the way, because I've seen some of these environmental problems be addressed. Another big one that's been addressed is ozone depletion. You don't hear people talk about ozone depletion that much anymore because chlorofluorocarbons were banned, and the ozone hole is much smaller than it used to be 10 or 15 years ago. And so we've really made progress on that. Now we just need to figure out this climate change thing, right? The climate change is our big issue of our day today, and it needs to be addressed. We're doing some things to address it. We probably need to do more, but I am, because I've seen these other environmental problems sort of improve dramatically, I have hope that we'll also make progress on climate change as well. We still have a ways to go though. Okay, anyway, that's not part of acids and bases, is it? Okay. Significant figures and logs are kind of a pain in the butt. I'm not going to worry about it too much. You can just follow the same significant figures rules that you've been following, but know that they are a little different for logs. I'm not going to count you off for that. You can read about it in the book if you're interested, but I'm not really going to spend a lot of time on it. Okay, so let's do an example here though. Calculate the pH at 25 degrees when the OH minus is 1.3 times 10 to the minus 2 molar. Okay, so if OH minus is equal to 1.3 times 10 to the minus 2 molar, right? Then what is the pH? Well, we know the definition of pH is equal to minus the log of H3O plus. So in order to get pH, we need to get the H3O plus concentration, but we know that H3O plus concentration times OH minus concentration is always equal to 10 to the minus 14, right? So H3O plus is equal to 10 to the minus 14 over the OH minus concentration. The OH minus concentration of this solution that we're trying to find the pH for, just plug that into there. So that's equal to 10 to the minus 14 divided by 1.3 times 10 to the minus 2, right? And that gives me 7.7 times 10 to the minus 13 molar. That's my H3O plus concentration. So my pH is equal to minus the log of 7.7 times 10 to the minus 13. Oops, sorry, not very clear. And that comes out to be equal to minus negative 12.11, which is equal to 12.11. Right, so is this solution acidic or basic?
Basic.
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 So notice there are four quantities that if you know one, you know all four, okay? They are H3O plus, OH minus, pH, and POH. And I haven't defined POH yet, so let me, shoot, those don't go in parentheses. POH is just minus the log of the OH minus concentration, okay? So it's the definition, it's like, so you can think of P as just being minus the log of, all right? And since H3O plus times OH minus is equal to 10 to the minus 14. If I take the log of both sides of that, I get log of H3O plus log of OH minus is equal to the log of 10 to the minus 14. And this log of 10 to the minus 14 is just minus 14, right? So then I can multiply through by a negative sign, minus the log of H3O plus minus the log of OH minus is equal to 14. And notice this is pH, so pH, this is POH plus POH is equal to 14. Okay, so the bottom line is this. If you know any of these, if you know any one of these four quantities, you know them all, right? And the four quantities are excuse me. If you know any one of these, you know all of them, right? Because if you know H3O plus, you can always get OH minus, right? Why? Because H3O plus times OH minus is always equal to 10 to the minus 14, right? And you can always get pH. Once you know pH, you can always get POH because they're always going to sum to the 14, right? So if pH is equal to 5, what's POH equal to? 7, right? So you can get any one of these. So part of your homework, you'll give you one of these and ask you to calculate the other 3, okay? Super straightforward. To get from between these two, you're going to use this equation. To get between these two, you're going to use this equation. Okay? Okay, I see a couple of questions and let's see, Ryland. Oh, no question.
You just answered it, actually.
Okay, all right, awesome. Yeah, the acids in soft drinks and everything else we eat that's acidic is all less acidic than our stomach. But eating too many acidic foods, and especially can, if you're susceptible to heartburn, can increase your heartburn, right? Even though the acids in our stomach are greater, it can contribute a little bit to that and give you heartburn. Okay, what else? Any other questions? As long as we're defining P scales, let me also define pKa because you'll see that as well. And if pH is minus log of H3O plus and POH is minus log of OH minus, then pKa is minus the log of Ka. All right, so you'll see that as well. In acid-base chemistry, these P scales are very common. So you'll be seeing them. Those are the 3 main ones, pH, POH, and pKa. Oh, I guess pK, well, we haven't talked about weak bases yet, but we haven't talked about bases yet very much. So let's see. This is pK, so nothing new there. Okay. So next is that. I don't think I want to jump into that yet because that'll take a little bit of time. So maybe I'll stop there. Quit a little early for a change. Doesn't happen very often. But maybe we'll quit 10 minutes early today. Are there any last minute questions that I can answer? And I'll stay on afterwards, of course, to answer any other questions you might have. But are there any questions anybody wants to ask now? Okay, I don't see any. So I'll go ahead and dismiss class.